Let me go ahead and show you in the LibreText section 4.6. There's a chart of some atomic sizes, the size of the atoms. So as you go down the periodic table, you can see that they get larger because you're filling up the next shell. We're starting the 2s shell with lithium, the 3s with sodium, the 4s with potassium, and so on. So as you go down the periodic table, you're building another shell, and that makes the atom bigger. Within, let's say, this period, this horizontal row, you are working on the 3 shell the whole entire time. And so as you keep building the 3s2, 3s1, 3s2, 3p1, 3p2, and so on, you are putting more electrons into the same shell. And at the same time, the nucleus is getting more and more protons, more and more positive charge. So that number 3 shell is getting pulled on by the positive charges tighter and tighter and tighter. So going down a periodic table, you are getting larger, but going across the periodic table, the atoms are getting smaller. So it's increasing going from right to left, and it's also increasing going down, the size of these elements. For ionization energy, 4.6.1 in your Chem LibreText, this particular chart we go over a little bit more in Chem 101, talking about removing the first electron, the second, the third. For this course, we're just going to worry about the first ionization energies. How much energy does it take? How difficult is it to remove an electron, one electron, from the neutral atom? So looking at these noble gases, helium to neon to argon and to krypton and so forth, the energy needed is going down. It's getting easier to take an electron away from these elements. And that's because these elements are getting larger. As you go down the periodic table from helium to neon to argon, the electron that you have to remove is further away from the positively charged nucleus. So as the atoms get bigger, the energy needed to take one electron away becomes smaller. However, going across the periodic table from, let's say, like we did before, from sodium going across to argon, these elements are getting smaller. The atoms are getting smaller, as we talked about in the previous section, that they're filling up the 3 shell, and the protons are getting more and more numerous in the nucleus. And so the size of the atom is going down, and the energy needed to take an electron away is going up, because these electrons of argon are closer to the positively charged nucleus than the electrons in sodium or magnesium are. And so it's harder as you go from left to right across the periodic table, the energy increases. So this is pretty much the opposite of the size. As things get bigger, it gets easier. As things get bigger going in this direction, it gets easier. So a larger atom has a lower ionization energy. It's easier to take the electron away. For metallic character in 4.6.2, we have this chart over here. So we just showed how the ionization energy increases going from left to right, but decreases going down, so it increases going up the periodic table. And that is how hard it is to pull an electron away from an atom. Metallic character is how easy it is to pull an electron away from an atom, because metals give up electrons fairly easily. And so this is exactly the opposite of the ionization energy. And it also matches the size, because we talked about how it's harder to pull electrons away when the atoms are smaller. It's easier to pull the electrons away when the atoms are bigger. So going down the periodic table, the metallic character increases, and going from right to left, the metallic character increases. So this element over here, it has the loosest grip on the electrons. It's the biggest one, first of all, so we have the biggest element here. The electrons around the outside are the furthest away. They're the easiest to pull off. They're the most loosely held. Going up to this corner, we have the smallest, tightest elements. holding on to the electrons the most, and the most energy is needed to pull the electrons off of the elements in this corner. The note packet doesn't have as colorful a chart as your Chem Libre text does, but hopefully it's a little bit easy to tell what I'm saying here. Going from right to left on the periodic table and going down the periodic table, you see an increase in atomic size and also an increase in metallic character. Going up and from left to right, you see an increase in the ionization energy. So those are the general trends in the periodic table. For the valence electrons, I will just use a real periodic table to show that. So the number of valence electrons an element has is the number of electrons that are in the outermost shell, the outermost orbital of that element. One way to figure that out is to look at the actual electron configuration of the element, but since most of the elements follow a pattern that is shown in the periodic table itself, there's a much easier way to figure out the valence electrons of most elements. I just wanted to point out that what I'm about to say does not apply to the lanthanides or the actinides. There are a lot of exceptions in the electron configurations down here, so if you wanted to know the valence electrons to one of these elements, you should probably just look up the electron configuration and verify that. So we'll go ahead and ignore the lanthanides and actinides and just look at the main part of the periodic table here, and mostly at the main group elements as well. Here, these elements are starting out a new orbital shell, a new level. So these ones have the very first electron being added to that level. So this family of elements has one valence electron. This one has two. Then the transition metals, remember, go one level down and start filling the d orbital of the previous shell. So in period 4, we have 4s being filled and then back to 3d. So none of those 3d electrons are in the outermost shell. They're one level down. So generally these have two valence electrons as well. There's a couple of exceptions, so I'll say generally two. Then this family goes back to filling up the p orbital in the outermost shell, so the third electron is added, and then the fourth, the fifth, the sixth, the seventh, and the eighth. So these main group elements, you can tell from the periodic table how many valence electrons are in their outermost shell. All of these elements are trying to get 8 electrons, because that would be a full and perfect shell. For example, the halogens, which have 7, gain an electron and become a -1 ion to try to get to have 8 electrons. So I just want to make a note that helium only has 2 electrons, so it does not have 8 electrons in the outermost shell. Helium only has 2. Let's go ahead and make a note of that. And all the rest of these have 8. So for hydrogen and helium, they are so small that they can only fit 2 electrons in their outermost shell. And so hydrogen with only 1 electron is trying to either lose that electron and have 0, or bond with something so that it can have 2 electrons in its outermost shell, not 8. Hydrogen and helium cannot handle 8. All right, let's go ahead and use this periodic table to answer 4.6.1 and 2. We're going to see which has the smaller size, the smaller radius. So copper is located here, and silver is here. And so going down the periodic table is where you get bigger. So the copper would be smaller, the silver would be larger. So the copper is smaller here. Then we have boron and carbon. Remember, going left to right across the periodic table, you get smaller. The protons are squeezing on that shell, so carbon is smaller than boron. Oxygen and phosphorus are located diagonally from each other, but oxygen should be smaller because it's higher, and it's also smaller because going to the left is smaller. sulfur would be smaller than phosphorus, and oxygen would be smaller still than sulfur. So for sure, oxygen is smaller than phosphorus. All right, we have sodium and potassium here. Sodium would be smaller. And then between lithium and beryllium, beryllium would be smaller. Remember, you're going smaller, getting smaller, going from left to right. So remember, the radius is getting larger, going to the left and down. The ionization energy increases, going up and to the right. So we want the lower ionization energy. That would be the larger atom. So that's complete opposite of what was being asked for in 4.6.1. 4.6.1, we circled the smaller atoms. The lower ionization energy would belong to the larger atoms. It would be the opposite. So here we have silver being more below copper. We have boron being more to the left of carbon. We have phosphorus being below and to the left of oxygen. Potassium being below sodium over here. And lithium being to the left of beryllium.